Imagine a world without smartphones, laptops, or even pocket calculators. That was the reality before the transistor. Electronics relied on bulky, inefficient vacuum tubes. These glass tubes, often as large as light bulbs, controlled the flow of electricity. However, they had serious drawbacks. Vacuum tubes generated a lot of heat, like tiny ovens within electronic devices. They were also fragile and prone to burning out, much like old-fashioned light bulbs. This made early computers massive, power-hungry, and unreliable. Clearly, a better solution was needed. The world was on the cusp of a technological revolution, waiting for a breakthrough. Little did anyone know, a tiny device would soon change the course of history. The path to the transistor began with a curious observation. It was a journey that spanned decades and involved the contributions of many brilliant minds. Thomas Edison, the famed inventor, noticed something unusual in his incandescent light bulbs. This observation would lay the groundwork for future innovations. A current seemed to flow between the heated filament and a separate metal plate inside the vacuum. This was more than just a quirk, it was a phenomenon waiting to be understood. This phenomenon, later known as the Edison effect, hinted at the possibility of controlling electricity in a vacuum. It was a small but significant step towards the development of electronic devices. John Ambrose Fleming, a British scientist, built upon Edison's work. He saw the potential in Edison's discovery and took it further. He invented the Fleming valve, also known as the vacuum diode. This invention was crucial in the evolution of electronics. This device allowed current to flow in only one direction, acting as an electronic switch. It was a breakthrough that paved the way for more complex electronic circuits. Meanwhile, another intriguing development was taking place. Scientists were exploring the properties of semiconductors, materials that would become the foundation of modern electronics. Early radios used cat's whisker detectors, crude devices that relied. Semiconductors, unlike metals, are not good conductors of electricity. Metals, such as copper and aluminum, allow electrons to flow freely, making them excellent conductors. However, semiconductors have a unique property that sets them apart. Nor are they perfect insulators. Insulators, like rubber and glass, prevent the flow of electricity entirely. Semiconductors, however, occupy a fascinating middle ground. Materials like germanium and silicon fall into this intriguing category. These elements have just the right number of electrons to make them versatile in electronic applications. Their electrical properties lie somewhere in between, making them ideal for controlling electrical current. This ability to control the flow of electricity is what makes semiconductors so valuable in modern technology. The key to unlocking the power of semiconductors lies in doping. Doping involves adding small amounts of other elements to the semiconductor material. By introducing impurities into the crystal structure of a semiconductor, scientists could alter its electrical behavior. This process allows for precise control over the material's conductivity. Adding certain impurities created an excess of electrons, forming an N-type semiconductor. These extra electrons are free to move, enhancing the material's conductivity. Others created holes where electrons were missing, forming a P-type semiconductor. These holes act as positive charge carriers, allowing for a different type of electrical conduction. The real magic happened when these two types were joined together, creating a PN junction. This junction is crucial for the operation of many electronic devices. This junction, with its unique electrical properties, formed the heart of the transistor. Transistors are the building blocks of modern electronics, enabling everything from computers to smartphones. After World War II, Bell Laboratories emerged as a hotbed of innovation. Scientists there were eager to find a smaller, more efficient alternative to the bulky vacuum tube. Three brilliant minds, John Bardeen, Walter Brattain, and William Shockley, joined forces to tackle this challenge. Their work focused on semiconductors, particularly germanium. They experimented with different configurations, trying to control the flow of electricity through these materials. The atmosphere at Bell Labs crackled with excitement as the team inched closer to a breakthrough. In December 1947, the breakthrough finally came. Bardeen and Brattain, working closely together, created the world's first point-contact transistor. This device, though crude by today's standards, demonstrated that it was possible to amplify and switch electronic signals using a solid-state device. The point-contact transistor consisted of a small block of germanium with two closely spaced gold contacts touching its surface. By applying a small voltage to one contact, they could control a much larger current flowing through the other contact. The era of the transistor had begun. Section 6: Shockley's triumph, the bipolar junction transistor. While Bardeen and Brattain celebrated their success, William Shockley, the team leader, felt a surge of both excitement and envy. Driven to make his own mark, Shockley immersed himself in research, determined to improve upon the point-contact design. His efforts led to the development of the bipolar junction transistor in early 1948. This elegant design, utilizing a sandwich of NPN or PNP semiconductor layers, proved to be more reliable and easier to manufacture than the point-contact transistor. It quickly became the dominant design for the emerging transistor industry. Section 7: From labs to living rooms, the transistor's rise. The transistor's impact on society was nothing short of revolutionary. Its small size, low power consumption and durability opened up a world of possibilities for electronic devices. The first commercial applications appeared in hearing aids, taking advantage of the transistor's ability to amplify sound. In 1954, Texas Instruments introduced the first commercially successful silicon transistor. Silicon, with its abundance and superior electrical properties, soon replaced germanium as the material of choice for transistors. That same year, the Regency TR-1, the first mass-produced portable transistor radio, hit the market, captivating the public's imagination. Section 8: A legacy of miniaturization and innovation. The transistor's impact extended far beyond portable radios. It paved the way for the development of integrated circuits, where thousands, then millions, and eventually billions of transistors could be etched onto a single silicon chip. This relentless miniaturization, driven by Moore's law, led to the exponential growth of computing power and the digital revolution we witness today. From smartphones and laptops to medical devices and spacecraft, the transistor is now an indispensable component in countless electronic devices. Its impact on communication, entertainment, healthcare, and countless other fields is immeasurable. Section 9: The transistor's enduring impact. The invention of the transistor was a watershed moment in technological history. It marked the beginning of a new era, revolutionizing the way we approach electronics and communication. Before the transistor, electronic devices were bulky, unreliable, and consumed a lot of power. The transistor changed all that, making it possible to create smaller, more efficient, and more reliable devices. It earned Bardeen, Brattain, and Shockley the 1956 Nobel Prize in Physics, a testament to the profound impact of their work. Their invention laid the foundation for the modern electronics industry, paving the way for the development of everything from computers to smartphones. The transistor's legacy continues to shape our world, driving innovation and transforming the way we live, work, and interact with the world around us. Today, transistors are found in virtually every electronic device, from the simplest gadgets to the most complex supercomputers. As we look to the future, researchers are exploring new materials and designs to further enhance the performance and shrink the size of transistors. Quantum tunneling transistors, nanowire transistors, and other cutting-edge technologies hold the promise of even more powerful and energy-efficient devices. These advancements could lead to breakthroughs in fields such as artificial intelligence, quantum computing, and the Internet of Things. And other cutting-edge technologies hold the promise of even more powerful and energy-efficient devices. The potential applications are vast, ranging from faster and more efficient computing to new medical devices and renewable energy solutions, pushing the boundaries of what's possible in the world of electronics. The ongoing research and development in transistor technology are crucial for the continued advancement of our digital age. The transistor, a testament to human ingenuity, remains a tiny giant, a cornerstone of modern technology. Its influence is seen in every aspect of our daily lives, from the devices we use to the infrastructure that supports our digital world. powering our technological present and shaping our digital future. As we continue to innovate and push the boundaries of what's possible, the transistor will undoubtedly remain at the heart of our technological advancements, driving progress and enabling new possibilities.
So hit that subscribe button, ring the bell for notifications, and let's turn the page on a new adventure together. Get ready to experience books like never before, only on VBook 360. Like, comment, and share to support the channel and keep the video magic alive. Thank you for stopping by. And remember, every video has a story, and every story deserves to be shared. See you in the next video.